So this problem is to find the 3 by 3 matrix that will rotate points 6 degrees around the given point minus 2, 3. So I'm going to give the most generalized solution using the given point as xy, since excuse me, it's not a linear transformation. We have to use the 3 by 3 homogeneous. So translation along the point xy can be represented by this 3 by 3 matrix, 1, 0, x, 0, 1, y, and 0, 0. And since we're at it, we also need the 3 by 3 homogeneous for translation along the point A, but back to the origin. So that's pretty straightforward. So it's 1, 0 minus x, 0, 1 minus y, and 0, 0, 1. And then, since we're dealing with 3 by 3, we have to represent the rotation of around the origin around 30 degrees. So this here is a matrix that represents rotation by theta about the origin and in the counterclockwise direction. And that would be cosine theta minus sine theta 0, 0, 0. So to represent the rotation around a given point x by an angle of theta, we have to first translate back to the origin using the green 3 by 3 matrix 1, 0 minus x. And then we have to follow that by the rotation around the origin, and then follow that back by translating back using the point A, right? So that means in terms of step by step, it's the matrix multiplication. First, by rotating back, translating back according to the point xy back to the origin, rotate around the origin by the angle of theta, and then translate it back to xy, right? So the result is the matrix multiplication, and that gives us the following matrix. Its first column is cosine theta sine 0, and then the second column is minus sine. And the third column is kind of convoluted because it's minus cosine times x plus sine theta times y plus x. And then finally, the second entry in the column is minus sine times x minus cosine y plus y. And of course, always the third entry is always going to be 1. Now, to check this, if we take an average, the point xy1, which should be invariant under this operation because that's the point that we're going to rotate. If we apply the product, so that gives us that. In terms of matrix multiplication, what we see is, let's see if I can represent all that in terms of matrix multiplication. So, I had the name for the matrix multiplication. That's translate back, rotate, then translate back to the point of A of the point in question. So let me see if that works. If that works, I think we hit it on the button in terms of the matrix. So I'm going to multiply that by this matrix here. And that should give us back, since this is a point of rotation, it should be invariant, right? So we apply that, it should give us x. So bingo, it double checks. So, and here's a couple illustrations, in particular asked for the point minus 2, 3, which is the point of rotation. And here's the point minus 1, 3 before it's rotated clockwise by 60 degrees, or pi over, in this case, pi over 3. So here's the, let's see, I think, okay, you see the point of rotation. So here's the, now after rotation, here's the point of rotation, minus 2. Here's the point in question, minus 1, 3, and it's rotate to this point here. Right? Matrix multiplication makes it very powerful because not only can you rotate points, say for instance, you can also, here's our point in question, minus 2, 3. And here's part of the parabola, because it's so small, it's just going to be looks like a straight line. If we rotate that part of parabola, we get this global picture, a little bigger picture of the result of rotating this part of the parabola to this. Now, the reason this is kind of off scale is because in this bigger picture, they have to expand the graph to visualize the net result of rotation, which is here. Okay, so that's straightforward. Oh, we almost hit it right under the button there. 5 minutes.